Hi everyone, I'm Xingda from Shanghai Jiao University. Today I'm happy to introduce our work on improving the performance of RDMA's control parts with a systematic approach. This is a joint work with my student Fangming and my colleagues Chen and Haibo. Remote directory memory access is a high bandwidth and low latency networking feature widely adopted in modern data centers. It provides two primitives. For one-sided primitive, the NIC can directly read-write server's memory by processing server CPUs. Two-sided primitive is a messaging primitive that provides the same receive interface. Thanks to RDMA, many distributed systems, including distributed key-value stores and distributed transaction processing systems, can have dramatic performance improvements. For example, Race Hashim, a recent production disaggregated key-value store, can execute a single key-value request within 5 microseconds. However, though RDMA's data path operation is extremely fast, RDMA's control path operation is orders of magnitude slower. Specifically, on our platform, we measure the end-to-end connection creation and connection time of a queue pair, which takes 15 milliseconds. In comparison, posting and pulling an RDMA one-sided requests only take 2 microseconds. More specifically, the RDMA control connection creation time can be decomposed into 3 parts. First, loading the driver context, which includes querying device status and creating the protection domain. Second, the application must create hardware queues, both at the client and at the server. And we need to connect these queues by configuring them to appropriate states. This time counts for 4 milliseconds. Note that to allow queue pair connection, different hosts must exchange connection information through the network, which counts up to 1 millisecond. From the above breakdown, we can see that the time is bottlenecked by the first and 2 steps. However, our analysis reveals that they are difficult to reduce. The time is dominated by creating and configuring hardware resources, for example, creating the hardware queues. One may argue that the control path costs can hardly affect the performance of traditional RDMA-enabled applications, including distributed KVS stores and distributed databases. This is because these applications run a sufficient long time, which amortizes the costs of RDMA control paths. Unfortunately, we find the control path costs may still affect new applications, especially those that require elasticity. One particular example is RDMA-enabled disaggregated key-value store. In such a setup, the nodes are separated in 2 rows, memory nodes. These are nodes with huge amount of memory with little CPU resources. They store the key-value pairs in their memory. Second, computing nodes. These are nodes that execute key-value store API on top of the memory nodes. They have little memory and has a powerful CPU. So they execute the key-value API by reading the key-value contents from the memory nodes using one-sided RDMA. RDMA-based disaggregated key-value stores provide elasticity by allowing dynamically adding and removing computing nodes. In the high loads, it can add more computing nodes to improve the performance. For low loads, it can reclaim the added nodes for better resource efficiency. For such a setup, we can see that new nodes need to dynamically create RDMA-enabled connections to the memory nodes. Thus, the high connection time of queue pair would inevitably increase the tail latency, especially under load spikes, which means there's a sudden increase of loads of the applications. So the goal of our work is to provide a systematic solution to reduce RDMA's control path cost from milliseconds to microseconds and being compatible to existing RDMA hardware and software. So to achieve so, our basic idea is to use pooling, which means that we cache the created QPs in a connection pool so that later applications can reuse the cached queue pairs as long as one is cached. For example, suppose application 1 started with an empty pool. It follows the normal RDMA control path, which is slow, and issues data bus requests after the queue pair is created. After it finishes, it can cache the queue pair in a connection pool. Afterward, a new application 2, can query the QP in the pool and issue RDMA requests to the cached one without creating and connecting the QPS. However, the approach has one important challenge. Different applications' QPM cannot be reused and shared. This is because RDMA is primarily designed as a user space solution, which means that QPS are not designed for sharing between them. So QP further has many complex data structures spreading over the kernel space and user space. Sharing all these features and coordinating between accesses of different applications, we believe is impractical. Further, sharing QP alone cannot eliminate the driver loading costs in the user space RDMA applications. To address this issue, our observation is that the kernel space RDMA, though less used, also provides full functionality of RDMA. For example, the user space RDMA QPM, namely IBV-QP, has an equivalent IBQP in the kernel, which supports all one-sided and two-sided operations. Thus, we can shift the application's RDMA requests to the kernel space QPS. Based on this observation, the idea is to cache kernel space QPS and put them in a kernel space QPS pool. Thus, applications can share and reuse these QPs since they share the same kernel. To allow the sharing, we will translate the user space RDMA request to the underlying kernel space QP request through system calls. Note that another benefit of a kernel space solution is that the kernel space RDMA avoids the costly user space driver loading process. This is because the kernel can preload the driver context during the boot time. Now, we allow different applications to share the QP to avoid creating them from scratch for new applications. So another problem we are facing is that how to reduce the QP pool size. So RDMA QP is a one-to-one mapping. This means that we need a dedicated QP to connect to a different server. Moreover, due to the high performance of RDMA, it is desirable to use different QPs per CPU to prevent locking overhead. As a result, each machine needs to cache n plus n QPS, where n is the machine number in the cluster and n is the core number at each machine to eliminate all the control plane costs. This causes a significant amount of memory used, especially for modern RDMA-capable cluster with more than 10,000 nodes. To address this issue, we find dynamically connected transport, a less used but widely supported RDMA transport with connectionless feature can help. Specifically, a single dynamic connected QP, DCQP, can connect to different nodes without a connection process as a normal RCQP. The hardware will piggyback the connection requests with the RDMA data path request, which is extremely fast. For example, a DC reconnection plus data operation only takes 3 microseconds. Notice that DCQP provides the same semantic as RCQP, which means that they also provide reliability. Based on the adoption of DCQP, the high-level idea is to reduce the QPS in the pool with DCQP. So we replace all the RCQPs with one DCQP. Consequently, the kernel can avoid storing all the QPS connections to all the other nodes. So one problem of using DCQP is that for each machine to communicate with a specific host, the host must create a DC target and hand off the target's metadata to the client, such that the client can pass this metadata to each RDMA request to indicate the remote host. So the question is that how can a client efficiently discover the DC metadata of a remote target? A naive solution is to use remote procedure call, RPC, for the query. So RDMA do provide unreliable datagram, which supports connectionless RPC. However, there are 2 drawbacks of an RPC-based design. First, RPC consumes extra CPU resources at each node. As a kernel-space solution, we cannot dedicate many CPUs to handle these requests. Second, RPC may incur long-tail latency due to the request queuing and the CPU scheduling at the remote host. So the desired way for the DCT metadata discovery is to use one-sided RDMA. So to achieve so, we propose an architecture that uses MetaServers to store all DCT meta-related data. So metadata is in principle similar to DNS servers that stores a mapping between a remote node's RDMA address and the corresponding DCT metadata. Notice that storing all the metadata of all servers in a cluster in a MetaServer is practical because the metadata is extremely small. It only consumes 12 bytes. So this separation allows us to use one-sided RDMA to query the metadata. Specifically, we implement the MetaServer as an RDMA-enabled KVS store commonly explored in the literature. The KVS store can be queried in one-sided RDMA by parsing remote CPU, which is extremely fast and resource efficient. Consequently, a whole connection and data process only takes 10 microseconds for new connections. So our final challenge I need to mention is that how to multiplex QP to multiple applications correctly. So to prevent a QP from not sharing, to prevent an application from not sharing a cache QP, we allow each DC QP in the pool to be shared among different applications. So we further abstract the shared QP so that it gives the application an illusion of an exclusively owned QP. For example, on application 1 and application 2, they have an exclusively virtualized QP at the user space. Nevertheless, the request to the virtualized QP can be forwarded to the same kernel space QP so that the applications can always have an available QP to use. However, one challenge of sharing the same QP among different applications is that the shared QP can be corrupted even when applications use it correctly, because they assume an exclusive owned abstraction. So if a QP is corrupted, it needs reconnection, which is slow. To this end, we carefully add checks before posting the requests to the underlying shared QP, and reject the requests that can corrupt the QP stats if necessary. Specifically, we check the following three things. First, malformed request. Whether the request contains an invalid operation code or a memory reference. Second, whether the request may overflow the hardware queue. Finally, we need to additionally dispatch the requests from different applications to the correct from the correct destinations, because the shared QP's responses may belong to different applications. So after checking all these factors, we can now provide an exclusively owned QP abstraction to the application for the shared QP without worrying about QP corruption. So put it all together, we present KRCore, a networking library that provides a microsecond-scale RDMA connection establishment. On commodity RNX that supports DCT, KRCore is 1,500 times faster than IB verbs, the de facto standard library for using RDMA. So you also apply many optimizations to further improve its performance, including DCT metadata caching and dynamic switch between DC and RC QPs. So if you have interest, please refer to our paper for more information. So to ease development, we implement KRCore as a loadable kernel module using more than 10,000 Rust lines of code. We further add a little C-shame layer to abstract the system core code for the KRCore kernel. So to support DCT in the kernel, we also port the user space DCT driver implementation into the kernel space RDMA driver by adding about 250 line of C code to the Linux OFED 4.9 driver. So KRCore is available on the GitHub. So finally, we present the evaluation results of KRCore, aiming to answer the following three questions. First, how fast is KRCore's control plane? Second, what are the costs added to the KRCore's data plane? Third, can KRCore benefit existing applications that require elasticity? Our evaluations are conducted on a local rack-scale cluster with 10 nodes. Each machine has one connect-X4 InfiniBand 100 gigabytes RNIC. So we compare KRCore with two counterparts. First, IB verbs is the de facto user space standard for using RDMA. Second, Lite is the only kernel-space RDMA solution that leverages kernel-space RCQP for communications. So first, let's examine the control path performance of KRCore. Our first case study is the performance of multiple clients connecting to a single server. So from the figure, we can see that KRCore is orders of magnitude faster than verbs and lights. Notice that the axes are log scale. This is mainly due to the fact that KRCore replaced the control path operations with data path operations, namely one-sided RDMA requests to curl the metadata to the MetaServer. Lite is faster than verbs because it avoids the driver loading process, since it's a kernel-space RDMA solution. However, both Lite and verbs are bottlenecked by creating hardware queues on the RNIC. Next, we present the performance of creating full mesh connections for a cluster of machines. You can see that KRCore also takes orders of magnitude shorter time than Lite and verbs respectively, thanks to the faster performance of connecting one connections. So KRCore traces the performance of data paths for faster control paths. Now we show its data path performance on a synchronized one-sided RDMA read benchmark. The client keeps sending one-sided RDMA read requests to a server in a run-to-completion way. So we conducted the experiment by increasing the number of clients. As we can see, both KRCore and Lite has a latency increase compared to RB verbs. The overhead has two parts. First, they have like 1 microsecond latency increase due to the system call overhead, since we need a kernel space QPR pool to share QPs between different applications. Second, KRCore has a slower peak throughput due to the introduction of DCT. Compared with RCQP used in Lite and verbs, DCT has a reconnection message, so its peak throughput is slower. Finally, we show that KRCore can benefit existing RDMA-enabled systems that require elasticity. We choose race hashing, a production disaggregated RDMA-enabled KVS store. At time 0, there's a load spike in the workloads. Therefore, race will dynamically spawn new computing nodes to accelerate its performance. So KRCore can bootstrap all the nodes within 1 second, thanks to its fast control path. In comparison, verbs and lights take several seconds to finish the connection. Note that initially KRCore has a lower throughput than verbs because DCT is slower. Nevertheless, we apply an optimization to dynamically switch from DCQP to RCQP in the background for the applications, and can regain the high performance which is similar to verbs. Notice that Lite is slower than verbs and KRCore at the final time because it doesn't support a low-lift RDMA API, which is necessary for applying various RDMA-enabled optimizations exploited by race. So in summary, KRCore is a microsecond-scale RDMA control plane for creating RDMA-enabled connections. KRCore achieves this by retrofitting DCT with kernel-space RDMA connection pool. KRCore has a slower data path and thus is not suitable for all the applications. Yet we have shown that it can benefit existing RDMA-enabled applications that require elasticity. So in conclusion, we present KRCore, a microsecond-scale RDMA control plane on existing RDMA hardware and software. We show that KRCore can benefit existing RDMA elastic applications, including RDMA-based disaggregated KVS store. We hope KRCore can further benefit more applications, for example, RDMA-enabled serverless computing. So thanks for your listening.